Hello and welcome everyone. I am Nitin from BTech second year Data Science and Artificial Intelligence branch in IIT Roorkee. Today I am going to discuss the topic of rank nullity theorem in applied linear algebra. So let's get started. What's next? Here are some topics we are going to discuss in this video. First, first of all, I am going to discuss the definitions of rank, null space, row space and column space because without these definitions we cannot proceed further. Then we will discuss about the rank nullity theorem, its proof, its mathematical examples and how we can use it. Further, we are going to discuss the applications of this theorem in real life problems. Rank nullity theorem is a basic result in linear algebra. It gives information about the relationship between the dimensions of row spaces, column spaces, and rank of matrix. In upcoming slides, we see how these terms are related with null space and nullity of a matrix and many more. Row spaces span of row vectors of a matrix and column spaces is a span of column vectors of a matrix. Now take a matrix of m cross n. Here u1 u2 up to um are row vectors and v1 v2 up to vn are column vectors of a matrix. Now the set of all the linear combinations of u1 u2 up to um is called row space and the set of all the linear combinations of v1 v2 up to vn are called column spaces of a matrix. Null space. Null space is set of all vectors that mapped to zero vector when linear transformation is applied. It's like solution of equation ax is equal to 0. We can also understand it like we have given a linear system of equations where we get the form ax is equal to b and now put b is equal to 0 vector in that equation, so we get the null space of that matrix. Nullity is the dimensions of a null space of a matrix, or we can also say the number of basis vectors present in null space, and the number of vectors other than basis vectors that present in null space are free variables, and those free variables can be obtained by the linear combinations of these vectors. We can get to know more about the null space and nullity by example that are taken after the theorem. The statement of rank nullity theorem states that the sum of rank and nullity of a given matrix is equal to number of columns. For let a given matrix of m cross n, rank is defined as the number of linearly independent rows and nullity is defined as the number of non-zero columns in row reduced echelon form, and clearly their sum is equal to total number of columns in that matrix. Here rank and nullity is defined in more simpler ways. Rank is number of non-zero eigenvalues of a matrix and nullity is number of zero eigenvalues of a matrix, and sum of number of non-zero eigenvalues and number of zero eigenvalues is equal to total number of columns in that matrix. For proof of rank nullity theorem, take a matrix of order m cross n and make two cases when matrix A is singular and when matrix A is non-singular. In first case, when matrix A is singular, its rank less than order or we can say rank is less than number of columns. Let R be the rank of matrix, so number of non-zero rows in a row reduced echelon form of matrix is R. When R be the rank of matrix, then n minus r columns exists in matrix that contributes to the solution Ax is equal to 0, and the number of columns that contributes the solution Ax is equal to 0. This means nullity of matrix A is n minus r. Now when we add rank r and nullity n minus r, we get rank plus nullity is equal to total number of columns n. When matrix A is non-singular, its rank is equal to order of matrix. It means in a row reduced echelon form there are no zero rows in matrix, and Ax is equal to 0 has only trivial solution. So its rank is equal to order of matrix and nullity of matrix A will be 0. So also here we can prove that rank plus nullity is equal to number of columns. Now for further information you can get to the link provided here. Now let's take an example, a very simple example to verify rank nullity theorem. Take a matrix A of order 4 cross 3, and we have to verify rank nullity theorem for this given matrix. In solution, change the given matrix into row reduced echelon form step by step. Using elementary row operation, convert the given matrix into row echelon form. By applying these two transformations, we get matrix A here, and now further convert this matrix into row reduced echelon form. Now we get a new matrix A, which is the row reduced echelon form of given matrix. Here we can see the number of linearly independent rows or number of non-zero rows is 2, so rank of matrix is 2, and nullity of matrix is 2, means these two columns are responsible for the solution of equation Ax is equal to 0. Here we can simply verify that number of columns is equal to rank plus nullity, as total number of columns is 4 and rank 2 and nullity 2. So 2 plus 2 we get 4. Hence rank nullity theorem can be verified. Let's take another example where matrix A is given of order 4 cross 3. Matrix is 1, minus 2, 0, 4, 3, 1, 1, 0, minus 1, minus 5, minus 1, 8. First of all, convert the given matrix into its row echelon form, and the process of converting A into its row echelon form by elementary row transformations is given in example 2 PDF. It's very simple process. After getting row echelon form, we have four variables. We have these four variables and only two equations. We have only two equations and four variables, so there must be a condition where we have to choose two variables ourselves, and these two variables are called free variables, and these free variables came from the columns C3 and C4, as the columns C3 and C4 can be obtained by the linear combinations of column 1 and column 2. Now choose the free variables x3 and x4. These two are, we get these two conditions where we choose, in first condition we choose x3 is equal to 1 and x4 is equal to 0, so we get another two variable x1 and x2. In second condition we choose x3 is equal to 0 and x4 is equal to 1, so we get x2 12 by 7 and x1 is minus 4 by 7. These can be calculated from these two equations. We cannot choose x3 and x4 both 0 at the same time because it does not give any solution, or you can say it gives trivial solution 0 0 0 0. And the reason of choosing these free variables 0 and 1, it is because these, the variables as x 0 and 1 gives some important results in further studies. Now we proceed further to calculate the null space and nullity of this matrix. As we have discussed in the previous slide, that the number of linearly independent rows is 2, so rank of this matrix is 2, and there are two basis vector of null space, so nullity of matrix is 2. Now here we can also verify the rank nullity theorem, that rank plus nullity is equal to total number of columns. So there are 4 columns in the given matrix. Here null space, these are two vectors that represent null space that we discussed in previous slide. Now there are infinitely many solutions, but all can be obtained by linear combinations of these two null spaces. As we see in previous slide that x3 and x4 are free variables, so by changing those free variables we can get infinite number of solutions, but those all solution can be obtained by the linear combinations of these two vectors. So that's all. Now I think the concept of nullity and null space becomes more clear to you. Now in next slide we see how we can code for nullity and null space. This PDF consists of codes I have written for null space and nullity in Python. So let's see these codes. Here we have two codes, one for finding null space and second is for finding nullity. For null space we import matrix from SymPy library, taken matrix A 1 2 0 2 4 0 3 6 1 of order 3 by 3 as an example. Now by using the function null space is equal to a dot null space, we directly get the null space of matrix A.